Welcome to Wednesday. We are today Friday, then we're on our break for this one. Couple quick announcements. So we had a midterm yesterday. What did you guys think? Again, we're marking as quick as we can. We're doing our scanning and stuff. My goal is to get you marks, everything else back Monday at the latest, earlier if possible. But the plan is to mark through things tomorrow. I'll see if I can get things uploaded. The video lecture, apologies it didn't go up until last night, but it is online now. Please go check that one up. That's the content and topics from Monday. What we covered in that one is we're talking through nucleophilic acyl substitution, focusing on esters. That was a real deep dive because this ester conversion ends up becoming a core thing we do for a lot of different purposes. This is where we do things like saponification, transesterification, and most importantly, that bottom corner of our reactivity scale, accessing amides. Esters is one of the ways we can sort of go over to that one. So this is where we did the mechanisms of these components and other moments. So please do check that one out online. What we're going to talk through today is the other sort of transformations not contained there. These are things like tertiary butyl esters, and more importantly, jumping over to our acid chlorides. This is going from that middle tier of reactivity up to the most reactive compounds we have on our sequence. So just as again, from a localization, if you remember back before, we talked about alkylation to form esters. That's our alkylation and diazomethane reaction. That's taking carboxylic acids, nucleophilically grabbing some species to make our ester. The stuff in the yellow bar, that's the stuff content that we talked about in the video lecture. So this is Fischer esterification, lactonization, saponification. These are now the mechanisms of stuff we've talked through, but again, we're using that same categories that we talked about before. Acyl substitution falls into three kinds of general mechanisms: strongly basic, strongly acidic, and mildly basic. And these are different representations of those transformations. Today we're going to go in the bottom corner and talk about tertiary butyl ester cleavage. Again, this gets a special category because how this happens is unique to these T-butyl esters. It happens under acidic conditions, and most importantly, track which bonds are being broken and formed. From the last time, if we're doing a normal ester cleavage, like I'm taking this ester here and I'm breaking it down to something else, most of the time when we're doing a nucleophilic substitution, remember, we start off with a nucleophile, which is attacking this center. You do your Tai Chi kind of move, and you're breaking this bond where all of that is the leaving group. That's the normal distribution we've been talking about for nucleophilic acyl substitutions. That's why they're that middle sort of bucket before. That is not how the tertiary butyl esters work. These guys are special. Normally, we're cleaving this bond. Tertiary butyl esters, that's the bond we're breaking there. If you track through, this oxygen, the piece that we're using for the hydrolysis, ends up on the tertiary butyl piece. The oxygen that started out here on the carbonyl remains on that carbonyl. So this is just tracking which bonds are being broken, and it's represented in the mechanism. Again, this is only possible if you have a tertiary butyl or a tertiary carbon in your ester center. This is really limited to something where you have that tertiary center here as your ester component or group. And again, how we do this or how we prove this off is usually done by isotopic labeling. If I had an isotope of my O18 in my water, I can find that the O18 isotope only ends up with my tertiary butyl group. So this is an acid catalyzed mechanism, but it's a different one. It's not really formally nucleophilic acyl substitution. It's in the same area because we're doing transformations of esters, but it's a slightly different transformation. Now, quick quiz, I guess, about what do you guys know about tertiary butyl groups? There's a couple special things we can do with them. We can make, in particular, there's one very high energy intermediate that is uniquely stable if it's tertiary butyl. Think about carbocations. Primary carbocation, no good. Secondary carbocation, possible. Tertiary carbocation, you can use. That's what's happening here. Is this is because you're doing an acid catalyzed process. You're dealing with positively charged intermediates. And what we're doing here is we're actually invoking a carbocation. That's why this only works with these tertiary centers. How the mechanism works starts off similar to what you've seen before. We're going to activate the carbonyl. So by doing this, we're going to start off by protonating my carbonyl. O plus, O, and I'm going to highlight that fragment. Now by doing this, the first thing we've done now is, yes, I've made that center more electrophilic, right? I've actually taken that center and I've made it more electrophilic. This is the opening move for what we've done for acid-catalyzed saponification or cleavage. The thing that's different here is you can kind of think of it two ways. Yes, I've got water. Water could. The normal mechanism would be that water would attack. That's our normal acyl substitution. But if I go that route, I'm going up, I'm going to be coming down, I'm breaking this bond. That's the consequence of the nucleophilic substitution part of it. That's not what's happening here. Here what we've got is a competition between, yes, nucleophilic substitution could happen, but look at this group right here. I can draw this as a resonance structure. All I'm doing is I'm just pushing out charge. I want to isolate or highlight that I could draw this like this. Doot, doot, doot. O plus. This is just a resonance structure. What I'm highlighting here is the oxygen plus exists on either of those two oxygens, not just the protonated one up at the top. I can draw it where it's actually centered or right next door to my tertiary butyl group. So it's intramolecular. It's part of the molecule. All I'm doing around is moving my pi electrons. Because of that, it's actually really easy to break this bond and satisfy that charge, right? If I were to go this way and actually break this bond across here, what that generates is OH, double bond O. That's that sort of fragment. And over here, that becomes my carbocation. You could do the same thing from this other resonance isomer. All I'm doing is satisfying that charge. You get the same products from that one. So it doesn't matter which resonance isomer you want to draw it from. I'm just emphasizing it with the one on the right versus the one on the left. Again, what's happening here? You protonate your carbonyl. That's your opening move. Now you can think of it, you have a choice. Water has to act as a nucleophile, possible, or because you have that tertiary butyl group on that oxygen, you have the ability to blow that carbon-oxygen bond apart and generate my carbocation. Because that carbocation is tertiary, it's stable, intra wins out over nucleophilic. Yes?
Do you have to have a nucleophilic species, or can, if you were to do this with just an acid that doesn't have a nucleophile, will it just create carbocation?
Exactly. This works fine with just acid. I could take an aprotic system with HCl, protonate my carbonyl, and it will spontaneously blow that carbocation out. That's what makes this possible. We use this as a really, really important move for different peptide ligations, where just by treating with an acid of some component, the nucleophile is not really involved here. It's that protonation and then fragmentation which makes this possible. Now to finish off the mechanism, because I made my carbocation, I'm just going to redraw it over here. Remember, it's not done here. This carbocation is existing in solution where if I use something like H3O+, if it was in water, the solvent in that case is probably going to grab my carbocation. It's just grabbing this component, which gives me my positively charged intermediate. If water was to attack here, that becomes my charge carrier where I'm losing that proton back to, let's just say, solvent. Is picking off this proton to give me my final product. So the consequence, or what happens, the fate of this tertiary butyl group is it ends up being turned into tertiary butyl carbocation, and then usually the solvent, if it's water, if it's an alcohol, if it was chloride, whatever that last thing is going to grab that center, that carbocation, as my nucleophilic component. Again, this is only something that happens with strong acid in the presence of these tertiary butyl esters. Protonation of the carbonyl sets you up for the normal acid-catalyzed mechanism. Because we have this tertiary butyl cation that we can form, that fragments first preferentially, and then you're just capturing the tertiary butyl cation with whatever nucleophile present. Usually, we're doing it in acid and water. Water, the solvent, is our nucleophile, so we end up capturing it to make tertiary butanol from that one. And again, that's where that oxygen 18 label comes in. If the O18 was sitting here, that's the oxygen that sends up here. We're not substituting or migrating any of the oxygens from my starting material in this case. Okay, so now we've got that's our last transformation for our esters, is these two butyl cases. Remember, when we start off on a ranked order, these carboxylic acids, esters, they're sort of that third tier down. Remember, they had acid chlorides, anhydrides, our esters and carboxylic acids, and then down was our amides. So the problem we run into, and we've mentioned this a couple different times, is if I want to start off with these carboxylic acids, which are really useful building blocks, lots of times molecules exist as a carboxylic acid, but if I wanted to turn it into anything else, I'm really limited to what I can do. The carboxylic acid on its own is not a great group to use for nucleophilic acyl substitution. Any nucleophile will typically just end up doing simple acid-base chemistry in preference to our actual substitution. So I can't just do the easy thing of taking a carboxylic acid, a simple nucleophile, acid base is going to beat it every time. And remember, once that happens, not only have I quenched my nucleophile, it's not negative anymore, but I've also turned my electrophile, the carboxylic acid, into a carboxylate. It is negatively charged. It is not electrophilic anymore. You shut everything down here. So the strategy to actually do this is we've got to bring in our warp move now. This is where we have to take our carboxylic acids from that lower tier and then Mario warp whistle, take it back up to something up at the top. This is where we're going to be using the acid halides, thionyl chloride or PBr3, to convert these carboxylic acids into much more reactive systems. So we do this reaction to kind of format the carboxylic acid into a way better electrophile and then go and apply that electrophile. So we briefly mentioned this before. This was our sort of transformation. The analogy here is you guys have seen things like taking an alcohol into the chloride or taking an alcohol into a bromide. It's in that same genre where what we're doing is taking this OH functional group here. We're using a reagent. Each reagent is going to have the halogen that we're hoping to put into the molecule, and usually there's some kind of either sulfur or phosphorus reagent. That thing's job is to grab onto the oxygen and leave with the oxygen. So the mechanism behind them is very similar. Each one of these reagents is kind of this package deal of, number one, all the reagents we're using here are very good electrophiles. They all contain a sulfur or phosphorus. That thing's job is to grab onto the oxygen and pull it out. It's leaving with that. So if you look at your products, each one of those phosphorus or sulfurs is now attached to the oxygen species. So its job is to actually pull the oxygen out of the system. And each of these reagents has the electrophile or the halogen of interest that we're installing into our final molecule. So they have the same pattern where it's an electrophilic material that contains a halogen that's also doing a deoxygenation reaction. That's the general point. And again, if you guys remember seeing these kinds of things for tosyl chloride formation or chlorine formation, PBr3 to bromine, it's a very similar kind of overall process. We're going to focus in on just this mechanism. We're not going to look at the other ones. This is the only one we're going to do in detail. Now look at how it's set up. We're starting off with our acid. We're using SOCl2. The name of that is thionyl chloride. And what we're forming in the end is our chlorine in this position. That's where that chlorine came from, this group, or this reagent. The oxygen ends up leaving right there. And if you count out the other atoms, one of these chlorines is over here. That hydrogen is right there. So we've taken HO from our starting material. One of the oxygens ends up with the sulfur. One of the hydrogens ends up with Cl. You've got two chlorines coming in. One ends up on the carboxylic acid. It's now an acid chloride. One of them is departing as like Cl minus. Do you guys know anything about those three products? So acid chloride we've talked about. These are very electrophilic species. That's the target. That's the business end of what we're trying to do. HCl, what do you guys know about that? Strong acid, right? Chloride is a great leaving group. HCl has it's a very acidic media, right? Doing this reaction, you're producing HCl. Do you know what HCl, what is its disposition? If I were to give you a jar of HCl, am I handing you a liquid, a solid, or a gas? Gas, right? HCl is a gas. The only reason you guys have probably dealt with solutions of HCl, dissolves beautifully in water, right? High concentrations. But HCl as a reagent is a gas. What about SO2? If you had to guess, it's a solid, liquid, or gas. Yeah, you are making a gas and another gas on its own. Now again, solvent will help to take care of some of this. It'll help to dissolve these, or ionic compounds. But yeah, if you run this reaction in a solvent, not water, you will have SO2 boiling out of the system. You will have HCl boiling out of the system. It will melt your face. This is a very, very, very product-driven reaction because you are taking two liquids, or a solid and a liquid, and you're making a huge amount of gas. This is entropically favored. It's leaving the system, so it's energetically favored. You've actually got Le Chatelier helping you out because you're boiling out the gas from this one. That's why this was built this way, is we're taking every advantage we can to drive this reaction to completion. Now think about this again. Who's in biochem? Oh, you poor souls. Again, I am a biochemist. That was my undergrad degree. I can make these jokes. Do you guys know about ATP? Right? ATP is this is our universal conversion, or universal currency of energy. We take a whole bunch of reactions and we use them to make pyrophosphate bonds, which stores energy chemically for us to use later. That's kind of what you're doing here. You're taking a very high energy reagent, SOCl2, you're driving it to a really high energy product, the acid chloride, and you're paying that price by burning your SOCl2, your thionyl chloride, and you're driving the reaction forward with gas. This is the chemical equivalent, same strategy as how we do ATP formation, is we're forming a very high energy compound by coupling it to a lot of other product-driven high energy reactions. We're not beating thermodynamics. The price we're paying in this is really contained in the design of this starting material. Okay, so we're going to go through the mechanism. Now there's a couple of different ways of drawing this one. I'm going to show you one. I'm also going to highlight how the similarities and differences you may see online with their different sort of formation. In the end, what you've got to do here is I've got my carboxylic acid, my thionyl chloride. First thing I have to do is I'm bringing my electrophilic. This is a delta plus reagent. That means these guys are playing the role of delta minus. This is your nucleophile in this case. Now you can draw in a couple different ways. You could think about where what I'm doing is I'm using this lone pair to attack that sulfur center. And you can think of this kind of like a carbonyl, right? So if I do that addition, I'm punching up the electrons from that sulfur oxygen center. So it's very much like a nucleophilic addition to an acyl. We're just doing a sulfur oxygen double bond, not a carbon oxygen double bond as a result of that. So that's one way you can do this. The other way that you may see, instead of using just the lone pairs, you could also potentially draw this as the pi bond. Now why that matters is because if we're using the pi bond, we can couple it to this form here. This is another one they typically will highlight this particular transformation because this is a kind of a weird reaction we're doing. Not only are we doing a nucleophilic addition to a sulfur oxygen, what's happening here, and let me draw you out the consequence of these 2 points. If I go from this pi bond kind of addition, what I'm actually drawing is RO, double bond down here, hydrogen, with the plus center localized on that bottom oxygen, and I have now formed a new bond, to my sulfur. It's O minus, and I have chlorine, chlorine. That's kind of the sigma and pi bonding skeleton that I'm describing with these red arrows here. Now let's do the other one. If, instead, green arrows, I'm going to use just the lone pair. I'm going to attack that center, still punch this up. Same idea. I get double bond here, OH over to sulfur, oxygen minus, chlorine, chlorine, positive charge sitting down here. Are these two things different? Everybody's like, yeah, obviously, what's wrong with you? They're resonance isomers of each other, right? All that I'm doing to move between the two is if I take this double bond, or this lone pair here, if I bring it down and park the charge there, I get this resonance isomer. These are the same thing, right? So again, I'm just highlighting that some people, when they're drawing out this mechanism, they sit and subscribe to, oh, lone pair attacks versus pi bond attacks. These are the same overall transformation. You are activating the carbonyl with your sulfur electrophile, and you're ending up with this resonance stabilized oxygen point. Either of these is acceptable. You do not have to pick one or the other. But this is why these differences exist, is because, remember, the resonance structures are not fundamentally different from each other. Okay, what's the next move? Now that we've done this, what do you think happens? Now draw back what we've talked about with like nucleophilic acyl substitution. What do you think we do from here? We've just created something where you've got the sulfur oxygen, negative charge. We've activated the oxygen. What do you think makes sense next? Yeah. So bring down the negative charge in the oxygen? Yeah, what you've got, yeah, that's a good way of looking at it. What you have here, if you sort of focus on this center is kind of like your nucleophilic acyl substitution center. I've got a tetrahedral intermediate. If that was a carbon-oxygen bond with a chlorine, the next move I would do is I would bring down my negative charge to stabilize that center and eject my chlorine. And again, if either of these two structures are possible, I'm just going to use the one I've drawn down over here. So what that gives you, pretty irreversibly, R, double bond O, OH, sulfur, double bond O, chlorine. Okay? And you've got now Cl minus kicking out here. We're not done yet. We still have a positive charge over here. So in that context, drawing it in this isomer, where the positive charge exists next to this OH, makes it a little easier to see what has to happen here to get rid of that charge. The oxygen plus charge is satisfied by dumping that proton in the next step. Now we're getting to a neutral intermediate. So this is kind of, again, one of our first really weird things here. I've drawn this out where, drawing it in this resonance isomer over here where I've got this OH highlighted. I've kicked out chloride minus. What we have to do is I need to pick off that proton. This is how we might generate our Cl minus from this, or our HCl from this system. Does this feel weird to anybody? You're using chloride as a base, right? This is very strange. This is something that's usually sort of like, why do we do this? The reason it's possible here is, again, if you're dealing with high enough energy things, some of the rules have to bend. This is the matrix, right? You can break some rules and you can bend some rules. What we just did here is I've now made a molecule that looks like this, and I've made a single molecule of HCl. Yes, that's a gas, that might leave the system, but really what we're talking about in the context of this, I've got a super acidic proton. That protonated carbonyl group of that intermediate, the green one or the red one, losing that proton is much easier. Yes, chloride is present. We're just showing for atom balance that chloride could act as your nucleophile in this case. And again, it's only really allowable given the context of the energy that we're dealing with. We are talking about molecules that are ridiculously high energy. This is also like taking a mousetrap and winding up the sort of energy in the system so we can snap it shut. So now we've got this. And I want to redraw this in a slightly different geometry. So I'm just going to stretch out that molecule now as R, carbonyl, oxygen goes to sulfur carbonyl chloride. Does that look like a functional group you guys have seen before? This should remind you of something. If that sulfur was a carbon, what does that kind of look like? We've named that functional group. Anhydride? It looks like an anhydride. So what we just did is we started with a super electrophilic molecule, SOCl2. I used the carboxylic acid nucleophilically. I made a bond, and what I've just done is I made an anhydride-looking molecule. If this was a carbon, forget about an R over here, that's our anhydride core, which means I am super electrophilic at this center over here, right? This is a center where that is really delta plus. Yes, you have that on the sulfur as well. That's another consequence of this system, is over here, I also have a delta plus center. We're going to come back to that one later. But from a forward progress, I've made this center super electrophilic now. What we've done is a reaction we call Umpelung in some cases. Have everybody heard that German word? No, it's not from Willy Wonka? No. Umpelung is a German word that means to reverse. What we did is we took a nucleophilic species, the carboxylic acid, and we just turned it into a very electrophilic species, this anhydride. We switched the polarity to allow the reaction to happen. Now, the other way, instead of drawing this HCl as this, remember, HCl, you can represent it as H and Cl minus. It is this ionized species, which means if I form this super electrophilic species and I need a nucleophile, well, chloride's the best bet I've got in this system. I can actually sit here in this super high energy electrophile. The next sort of finishing move I can go across here, I can bring my chloride back into this system, and I'm doing the same move I would use for my nucleophilic substitution with a negative nucleophile. Remember, if this was an ester or some other simple compound, like maybe an anhydride, if I had an alkoxide, RO minus, what I would do is take that O minus, attack my carbonyl, punch it up to make a tetrahedral intermediate, bring it back down, kick out my good leaving group. What's different about this is the nucleophile here looks super, super sus because, dude, it's chlorine, but it's still negatively charged. And the only reason, this is where pairing matters, is chloride is not usually a nucleophile we're ever going to consider, but it is negative. This electrophile is so much more electrophilic than what we are going to. You are at an energy surface where you're so high up that even chloride is a good enough nucleophile to let this reaction happen. That's why we've engineered it this way. There's one more feature that makes this possible. So I'm going to grab this. I'm going to try to grab this. And we're going to take it to the next page, and we will complete this. So copy, paste. This is the step we just did, and I'm going to draw out the product from it. What I'm saying is we have our R, we have our O minus, we just brought in chlorine and O, sulfur, oxygen, and one more chlorine over here. And remember, we still have a proton swimming around in solution. That's just our charge balance. Okay, now that we've got this, we are set up for our final finishing move here. If you look embedded, we have our acid chlorides kind of chilling out right there. That's the acid chloride piece. That is what? SO2 and Cl minus. That's the last bits of fragmentation we have to have in the system. So what you can do from here is a couple of different points. From here, if I bring this charge down, this is the other half of the sort of the nucleophilic or carbonyl Tai Chi, we can bring that bond over here. That's going to form a new oxygen-sulfur bond. As we do this, remember, sulfur in this oxidation state, this is sulfur 4. I only want 4 bonds to it. By doing this, bringing in that bond, I've got to kick something out. Now you could draw this in a couple different ways. In the end, if I'm bringing in this bond here, it's like I'm kicking up over there, right? So let me draw just that for a second. We now have formed our carbon-oxygen double bond. We've got our chlorine sitting over here. The fragment we've left over is going to be oxygen, sulfur, O minus, and we have a double bond that we just formed right there. And the last piece is our Cl. So to get to our the SO2 as the gas, all we have to do is bring this down, kick that group out. That gives us our sulfur, double bond oxygen, and double bond oxygen, Cl minus. So now in this mix, we have all the pieces we have. Cl and H, there's our HCl component. We have our SOCl2, and we have our acid chloride. Those are the different pieces that come together. And again, what makes this reaction move forward, we're doing a couple moves that seem, again, super sus. Chloride is a nucleophile. Why? Way powerful electrophile. This isn't just an anhydride. This is some weird, funky sulfonyl anhydride. Yeah?
Would it be wrong to, as we're making the second SO double bond, to in that step kick off the chloride?
So just, yeah, let me show you that. What you're saying is, if I do this and that, that's also fine too. All we're doing, this hiccup in between, I'm trying to give you an analogy that looks like the carbonyl chemistry you've seen. So if we're pushing into a center that has a carbon-oxygen pi bond, typically we're going to kick it up and then bring it down again. Remember, this is just enforcing the Tai Chi type move. What do you mean? Sorry. Oh, so again, do not worry. Equilibrium versus straight, I do not care. Like, that is the major point. Theoretically, every reaction is reversible. I'm not going to grind that part. That is not an important thing. Don't freak out. You should be able to look at this and implicitly, which side of the equilibrium is going to be favored. A lot of the times they're equal balance, but this last step here, where we're generating SO2, you are making gases which are leaving the system. So I'm emphasizing that is going one way. You are not coming back once you make those gases. They are gone. But implicitly, it doesn't matter. I'm not going to grind you for, oh, you should have been in equilibrium. That's, again, what I'm trying to emphasize here, this is the ChemDraw version of it. This is the one that you probably see in your text. Now, depending on which text you have, like I said, the variations you'll see about this mechanism, sometimes people draw it as a pi bond attacking versus a lone pair. Those are just resonance isomers of each other. Once you have this, you're doing a collapse of that. The tetrahedral intermediate this gives you back your first chloride. Super weird move, chloride acting as a nucleophile. That is weird about this system and only allowable because you've made a ridiculously electrophilic system. So it can either be a base or a nucleophile in this sort of context as you go through. Decomposing this fragment here to our SO2 is what gives us the main driving force of this reaction. You're breaking up that SOCl2 into SO2. And remember, that's also extracting the oxygen. The oxygen that started out as our starting material over here is ending up as a carbon-sulfur bond. That's where we're hiding it and removing where that atom ends up going. Okay? And again, this is a special set. We use this here because what we're trying to do is massively climb energetics. We're going from a relatively stable species uphill back to our acid chloride. Once we're there, this is super useful. So, if you look at this guy, acid chloride plus a sodium acetate or sodium sodium negatively charged carboxylic acid species, which mechanism do you think this follows? Strongly basic, strongly acidic, mildly basic? Which one can you eliminate from this series, probably? Ooh, strongly basic is out. Okay. I'm going to put that as a... What's another one you can definitely eliminate from this one? If I was, am I operating under strongly acidic conditions? If you look at the arrow, do I have like HCl or something in here? No, I am not using a strong acid. There's no like acid catalyst here. If you had an acid catalyst in the presence of a nucleophile like that, we would just do acid-base chemistry. That one's definitely out. Yeah, what you have here is either you can consider it as potentially mildly basic or strongly basic. If anything, remember, this is acting as, this species is O-. So remember, if you go back to your bin of what you have to get into different categories, do I have a really powerful electrophile? Yes, this is our best one. Do you have a really good leaving group? Do I have a negatively charged nucleophile? Strongly basic is probably what I mean. Again, this is not meant to be like, oh, quiz show. What I'm trying to bin in is the mechanism you expect for strongly basic. That's the really, really simple one. What I'm saying is the nucleophile is already negatively charged and ready to go. I don't have to prime it in any way. The electrophile is already charged, primary, ready to go. All I have to do is bring my negative charge into the system to do my addition. So the way that this mechanism is going to go, I start off with my negatively charged species. I'm going to attack my group. Remember, the chloride is going to be polarizing that center, making a powerful electrophile. My acetate, or my acetate anion, is going to end up being my simple nucleophile here. So that's going to give me O-. Your leaving group, your chloride, is still attached for right now. And we've just brought in our other fragment. That's our step one. That's the nucleophilic addition. And this is a simple collapse of that one. That anionic tetrahedral intermediate is going to bring that charge down, punch out the leaving group, our chloride. That's going to give you your R, double bond O, O, double bond O, OR prime. That's how we make our anhydrides from these systems. So we end up with just chloride minus here. And again, I've drawn this where obviously there'd be potentially a charge balance, you'd be coming in with like the sodium or a salt of this one, which means what we're making here is sodium chloride as our product. So this is why it's a simple two-step mechanism. This is why acid chlorides are awesome, because they're so electrophilic and the leaving group is so good, most nucleophiles follow this mechanism. Having an acid chloride means you're just doing addition, negative charge up, bring it back down, punch it back out. Very, very simple transformations. You don't have to go through these other activations and other components like we've seen with our things like our acids for Fischer esterification. So this is our try it later one. Again, go through the mechanism of this and form your product. Now, one other thing I want to mention is this is where we can do these transformations with our anhydrides. We'll talk about what we can do with those in a minute. The acid chlorides, though, can access any of the other tier that we've talked through. So this is acid chloride to anhydride. That's the first one we did. If we take our acid chloride plus an alcohol, we get to our ester tier. Acid chloride plus our amine, we get to our amide tier. So all of our particular different groups are accessible in this way. The one thing I want to point out about these systems is, remember, you're taking these groups. This is definitely your electrophile. They are delta plus at that carbon center, and they're really, really delta plus, right? The chlorine is pulling onto it. The carbonyl is pulling onto it. You got a good leaving group. That's the first step. Depending on what you're trying to make, if I'm making an ester, I go in with an alcohol. If I'm trying to make an amide, I go in with my nitrogen. The choice of your nucleophile tells you how to drop into these different systems. So it's just like if I'm making an acetal, I need my alcohols. If I'm making my imines, I need my amines. What is this junk? This junk here. You guys have seen those before. Yeah. It's a weak base to absorb positive charge. What, if I had to give them names, what is PYR? It is pyridine. NET3 is triethylamine. Both of these structures, if you draw them out, so pyridine looks like this. Triethylamine is ethyl, ethyl, ethyl. They both have lone pairs. They are not nucleophiles. We use these as obligate bases. We're saying all their job is to do is to pick up protons. They're not acting as nucleophiles because ideally we've got bulk or we've got something else about them that we're trying to lock them into a corner where their main job is act as a weak base. They're just there to pick up protons. Now, that matters because as this reaction runs, look at the other components. As I take the fragments I've drawn out here, alcohol plus electrophile, you are liberating Cl and H. There's one equivalent of HCl that's being generated from both of these two systems. That's why the base has to be here. If you just run this reaction where I take an acid chloride plus an alcohol, you will make an ester, but you're also making a buttload of HCl. And if this was in an environment where that HCl starts to build up, now you start doing a whole bunch of acid catalyzed chemistry. You can start to hydrolyze your ester. You can start to break it down in a bunch of different conditions. The last one's even more detrimental. As I build up HCl, HCl is going to start grabbing my nucleophile and just shut the game down. This is where we have to run these with one equivalent of a base to mop up the HCl that's being used. This is the consequence of using these acid chlorides. They're very good at sort of just binary comparison. I just nucleophile, electrophile. But always remember that these need some amount of a tertiary amine base, a weak base, to mop up the HCl that's in the system. Otherwise, you're going to have problems. So how this mechanism looks like, it's, again, similar to what we've talked about for our nucleophilic substitution under kind of got strong, think of it like a strong base kind of system. It's a very simple sort of addition. In the end, we're going to do a nucleophilic addition into my carbonyl. In this case, I would have my isopropyl, O minus, and Cl. The nucleophile is my OH here. Much like our imine additions, what we're saying is my nucleophile is already good enough for this particular electrophile. I can just bring the two pieces together directly. So like what we did with our aldehydes and our amines, we can just bring those two pieces together directly to make a zwitterionic compound. Now, once we have this, you could undergo 2 proton transfers What we're doing there in the end is I want to just balance out the charge of the system. What I'm trying to do is get one proton gone from here and one proton added back there. And again, I'm showing you the mechanism that's drawn out usually in your text. Isopropyl is now going to have our OH. We still have our chlorine attached. Actually, let's do that in green. And we're going to have our O-ethyl. All we're doing here is just balancing our charges back over. Now, another version of this, again, one thing you could do is just get rid of the proton on my nucleophile, leaving this negative charge in place. That's really the same thing. Either of those two mechanisms are the same. I just want to show you this one here because, again, this is usually what's posted out in your text. By doing those two proton transfers, what we're doing here is we're just getting back to an isoelectronic satisfying all charges. What we still have to do to finish this off is lone pair needs to come down. I need to reform my carbonyl bond, and I need to eject this leaving group. So I'm kicking out that group over here. That's going to give me isopropyl, OH plus, and your carbon fragment for your ester. And we've ejected from that our Cl minus. Because this reaction is being run with pyridine, the final proton transfer, we would say, is to our base. So our pyridine here, its job is to pick off that last proton. And again, it's probably what you'd be using in your proton transfer steps. It's the thing that's carrying the charge and picking up and dispensing protons as the conjugate acid base as this reaction runs. So that gives you this overall transformation. Like I said, if you choose or if you prefer to just do one proton transfer event here, leave that O minus and collapse it, 6 in one, half a dozen the other. Those are both the same mechanism. This is just the one which goes to an isoelectronic intermediate. Yep. That's our transformation for our esters. The amines, very, very similar. We're once again going in with our nucleophile, with our pyridine, and acid chloride, and it's going to follow that same transformation we laid out. Nucleophile is going to attack tetrahedral intermediate. In this case, we're doing our proton transfer shown here. We make that negatively charged species. This is the other version I mentioned for the oxygen center, where we collapse that down, kicking out the chloride to give our amides. So they're really the same overall general mechanism, and I'm just giving you both examples where we go from our anionic intermediate or the fully charged balanced one. Both of them are possible. All right, guys, I will see you on Friday.
Okay, so for these try it later problems, first one is we want to predict the organic product from the following reaction, drawing the mechanism. If you recognize this, we're using our carboxylate and our acid chloride. This is our electrophile. That is our nucleophile. So we're going to do the addition this way. That's our first step. Remember, this is kind of mimicking our strong base conditions. And in this case, the carboxylate is our nucleophile. After this, we're going to bring down this charge and eject our leaving group. So we're going to get, as our product, now our carbonyl is reformed, and we have this other fragment. You should recognize this as what functional group? Take a look at this. That functional group we refer to as an anhydride, right? But there's a special name we give to this on top of it. It's what we call a unsymmetrical or otherwise mixed anhydride. What we mean by that is the R group here and the R group here are not the same. The reason why that matters is if you imagine we took another nucleophile, let's say we're using this for the electrophilic coupling. A nucleophile could attack here or here, and those would give you two different products. The acyl group that gets transferred onto this nucleophile could either be from cleavage at this site, which gives you this fragment attaching onto the nucleophile, or this site attaching the nucleophile. Those are two different possible products. We'll talk about a little bit more about strategies of using mixed anhydrides in the coming lectures. But the thing to point out now is we call this a mixed anhydride because the R groups on either side of our anhydride core are not the same. It's not symmetric. Now for this product, we're asked to draw the mechanism following reaction. Once again, we're running this reaction with our sacrificial base, or pyridine, here to help with our proton transfer. But the first step will be the addition of our neutral nucleophile into our electrophile center. So that's going to be isopropyl. We're going to have our tetrahedral intermediate, chloride, and now our NHH, positive charge, like this, 2 carbons, 1, 2. Now we're going to use our pyridine, so I'm going to draw that out. That's our nitrogen center like this, and we will pick off one of these protons. That can just give us our acid-base reaction, giving us our isopropyl, our O-, chloride, and our NH with our 2 carbons still attaching. Now from here, we're going to bring down this charge and eject the nucleophile to give us our final product. Remember the other thing here for charge balance, this reaction is going to be running with pyridine, where we're making one equivalent of the pyridine salt and chloride minus, just for balancing out where all the atoms go in this transformation.